Hello, welcome to Water Resources Management. This video goes through the notes for Lesson 1, which is pretty much the introduction to the course. Now on the Moodle website, which is the subject of another video, which should be watched first, it will show you how to get to this one. By way of introduction, it's the usual first class meeting with a review of the syllabus, a tour of the website, and then some definitions and concepts. The syllabus review is handled in a separate video, and that is also accessible through the learning management system. The website tour is also the subject of another video, managed again through the learning management system. Because the use of a learning management system is an experiment for me, the website tour in this video will actually access both the learning management website as well as the current backup archive. The intent for the class is you will access the content through the learning management system. It has the ability to track your access and track your homework assignments and your other activities. The archive website is more for my use to maintain an archive of most of the content, as well as in the off chance that the learning management system database crashes but the server continues to run, you can still access many components of the course. What you cannot do without the learning management system is to upload homeworks and projects and so forth. So water resources management can be defined as listed here as the activity of planning, developing, distributing, and managing the optimum use of water resources. Water resource management planning considers competing demands for or on the water. Examples of demands for water are quantity, location, and timing, and demands placed on water are its ability to assimilate waste materials, and that affects the quality. The two don't necessarily have to be distinguished. And the management seeks to allocate that water on an equitable basis to satisfy all uses and demands. Now that's a very nice sounding goal, but it brings with it some challenges. The word allocate means 1. To apportion for a specific purpose or to a particular persons or things, distribute or allocate tasks among human and automated components. So that's one definition of allocation. It actually has two parts to it. The second one I found when I looked up on the electronic library known as the Internet is to set apart or earmark, to designate or allocate a section of the building for special research purposes. So both definitions are in use in our common daily experience. For instance, a laboratory in the Merck Center is allocated to a particular research professor. And as long as that professor is here, then that area is set apart or earmarked for their use. That's one type of allocation. The other one is to apportion for some specific purpose some tasks. So for example, when you did team design, each one of you was assigned a different task. You were allocated a task and presumably all brought together to satisfy the goals of the team. And where this matters is that we're dealing with water, and it's a relatively scarce resource, at least at the quality that we need for modern civilization. And because it's scarce, both in place, time, and quality, the allocation, the act of allocating the water, will necessarily deny the resource to some and supply it to others. So some people that want the resource won't be able to get it. And that is the essence of the challenge of water resources management. The other word that appears in the original definition is equity or equitable. Now the definition of equitable is listed here. Having or exhibiting equity, classic definition using the word you're trying to define, so that would have failed us in grade school. Dealing fairly and equally with all concerned, an equitable settlement of a dispute. Second category is existing or valid in equity as distinguished from law and equitable defense. So equity is some kind of fairness. So because the resource is scarce, we've already stipulated that the allocation will necessarily deny the resource to someone and supply it to others. The concept of equity implies that that allocation occurs in some context or some architecture of fairness with respect to that allocation. So equity and allocation are a big part of water resources management. To make that allocation, we have to make decisions. In some instances, that might be an individual decision maker. There's some purity and clarity to that in many contexts. Alternatively, there's collective decision making, and that's more the norm, certainly in water resources management. An individual decision maker can be a king, a dictator, an owner of some resource, and it's up to that one person or entity, if the individual is actually the legal entity called a corporation, to make the decision, and they can make the decision any way they damn well please. Collective decision makers also, in theory, could make the decision any way they damn well please, but generally they're constrained by policies to make a decision that is beneficial in some context. So let's look at the act of decision making. Some people can seem indecisive or inconsistent. That would certainly define me in many aspects of my life. They avoid making decisions as long as possible. It's called a procrastinator, and it follows the theory that a problem ignored might go away. Oftentimes that burns you. The same reluctance to make decisions happens in organizations or institutions all the time. We have examples of that here at Texas Tech. You probably have examples of that from your work lives. Because decisions allocate something that's scarce, there's a natural human tendency to delay that in order to essentially allow the decision to be made by someone else, or for the decision to perhaps go away because one of the demands on the resource overnight disappears. Okay, so that reluctance can occur in organizations, institutions. On the other hand, there's some people that will make a decision without even thinking about it. Call them accused of leaping to conclusions or making a decision without considering all the facts. And that too is quite common. And on an individual basis, it probably reflects our individual assessment of how consequential or important that decision is to us. Either of these contexts is important because it implies that decisions, certainly in the water resources arena, should be made by collecting and weighing the various elements in some rational fashion. An important note here is that there is no decision making to be done if there's no alternatives. So there have to be alternatives, otherwise there's no decision to make. Or you can put that cynically as, the simplest decision is the take it or leave it decision when you have no real choice. Even I guess there is a decision to take it or leave it. There's certain instances where there is no decision to be made. As a hypothetical, for instance, you're on a transit from Earth to Mars. You're the first group of colonists. The spacecraft you have is going to take you 2 years to get there. everything's all happy, and then a microasteroid miraculously manages to pierce the skin of the ship and literally hit every freshwater storage tank on board, every single one. The water leaks out of the ship quite quickly because naturally you're asleep when it happens. And when everyone wakes up and the alarms are pounding and they regain pressure, they realize there's no water left on board except the water that's in one person's canteen. There's not a whole lot of decision making there on allocating that canteen full of water, because you're all going to perish anyway. What it really comes down to is someone's going to perish a few hours later than the remainder. And that's probably going to be the largest person who beats everybody to a pulp to get that one thing of water. That's a case where there's no real alternative. There's not much decision to be made. Although I suppose the astronauts could make the decision of whether to die of thirst or elect to go into the airlock, depressurize, and pretty much fall asleep because of hypoxia. Not that I'm encouraging anyone doing suicide. I probably would choose to go of hypoxia rather than thirst. So how do people make decisions? Well, that's actually a subject of a whole host of business scientists, if you can call business science a thing, psychological, and some extent psychiatric, because the decisions are made by people. There's psychology, business, and there's also going to be brain chemistry involved. The psychological aspect is an important part of decision making because it can override any rational process. People's choices depend on how alternatives are presented. So the cartoon in the right side of the figure shows a couple of cases. Let's look at just the upper row. Okay, in both the upper and lower row of the cartoon, there's two alternatives to be selected: alternative A and alternative B. That's all there is. There's the two alternatives to be selected. There is no do nothing alternative. One or the other path has to be chosen. In the upper one, if the decision maker chooses path A, there's a 100% chance that 200 people will live. So I don't know what the decision is. Let's go back to the spaceship thing. One tank was left. One water tank was remaining. We can choose one path. There's a 100% chance that 200 people live. Or we could choose path B, which provides a 33% chance that 600 people live and a 66% chance that 0 people live. Now let's look at the lower case. In the lower case, if we choose A, there's a 100% chance that 400 people are going to die. If we choose B, there's a 33% chance that 0 people die and a 66% chance that 600 people die. And in this particular context, the total number of people we're talking about is 600. So depending on an individual's aversion to risk and somewhat of an understanding of probability, this is a very difficult decision for many people to make. I too would find it difficult. Let's look at the upper row. So if I choose A, 200 live, 400 die. So I've saved 200 people. They're going to be my best friends. If I choose B, I have a 1 in 3 chance that 600 live and a 2 in 3 chance that 0 live. So there's a concept from probability and risk management called expected value. So in decision B, the expected value, which would be the sum of the probability times an outcome, the expected value of decision B is 1/3 times 600, which is 200, plus 2/3 times 0, which is 0, for a net expected outcome of 200 living. So the expected result of B is the same as the most assured result of A. So in terms of expected value, Um, one could argue that those two decisions they produce identical outcomes in a probabilistic sense. Okay, let's go to the lower one. Again, 400 die in decision A, and the expected value of death in decision B is also 400. So those two have identical expected values. Point is, in a probabilistic sense, those are the same um, expected outcome. Now I want to ask you, which decision would you make? Do you go for the sure thing, absolutely killing 400 people, or do you go for the 1 in 3 chance that everybody lives? It's a tough call. That's a tough decision to make. And it's emotional, and that's the point. There's a lot of emotion involved. Actually, at the moment of decision, it's purely emotional. The whole point of the tools explored in this course, they're tools to help support that emotional aspect, to allow us to actually make a decision rather than worry about the consequences of the decision going badly. And the life and death example shown here is intentional. It's intended to stimulate emotional response. Now, if we weren't talking about people, if you're talking about mosquitoes, it's a different thing, because our emotional attachment to the survival of a mosquito is much different than the emotional attachment to the survival of other people or of my pet cats. So what we've examined so far is that water is a scarce resource. We have accepted globally that we want to make that allocation fairly. To do an allocation, we have to make a decision. Decisions are made by people, and there's a strong emotional component at the moment of the decision. So the challenge of water resources management really boils down to a handful of things. First is to define what is fair for a particular situation. Secondly is to define alternatives. We have to find a decision point or decision plan. And then lastly, we implement tools to support the decision. And notice that word support. That's all the tools likely do. The tools are quite elaborate and complex. We're going to look at least get a flavor for linear programming and nonlinear programming, which are optimization techniques. And if we can cast a decision-making problem into a mathematical context that fits those, we can operate those tools and produce in a mathematical sense what would be the best decision. Again, we have to define what the merit function is for best. So that's the challenge of water resources management, is literally these 3 bullet items. So in the tools to support the decision, we have to find some way to value those alternatives. The value matters for measuring fairness as well as economic costs. We have to determine a policy to rank the values, and then a policy to guide the decision. Once that's done, we could conceivably hand the decision off to an algorithm, and that happens a lot in our daily lives. Using modern jargon, or at least cool-sounding jargon, that would be kind of a narrow domain artificial intelligence. Examples of that you've all experienced, whether you know it or not. When you're flying on a commercial aircraft, once the pilots get it in the air, most of the operation of that aircraft is handed off to a computer program. And they call it the autopilot. It's been well demonstrated for decades that autopilots can fly an airplane more cost effectively and more time effectively than a human being. Even the best human beings, they may be able to outdo an autopilot in an individual flight, but collectively they can't. That's a narrow domain artificial intelligence. It's taking sensory input, the The value it takes is what control command to issue to a control surface on the aircraft to keep it along its path. The ranking of the values is stay away from the edges of the air, because that's when planes and solids meet and they fall apart. And then the policy that guides the decision is the autopilot. So that's an analogous example to automated decision making. And there's quite a bit of aspects in our everyday infrastructure that would make a lot of sense to be handed off to a narrow domain controller. Once that controller makes the decision, it has to have a way to effect control. So how do we control a water system? We have a couple of, very much comes down to two things. An example is a SCADA algorithm that operates a water distribution network. That aspect of daily infrastructure can probably be fully autonomous and wouldn't take very much human intervention. We would want, as managers, to have some kind of kill switch. We'd want to be able to turn the automated controller off on demand and at the risk of causing a disaster take over control, especially if it's starting to do goofy stuff. But that's a case of complete control. In other instances, we have decisions that we make, but we really can't control the system. We can only provide influence. So an example of that is in water quality management. We have laws, and we can measure things, and we can issue fines, but it's really a voluntary compliance. And the source of water quality impairment is balancing the risk of apprehension versus the risk of doing nothing. So laws have influence on that system. Another example is tax codes. So a raising or lowering of a particular tax on something, think the tariffs, because that's in the news right now. It has severe monetary values involved, but it really influences the system. It doesn't establish control. Even with heavy tariffs, there's still going to be import and export going on to and from the United States. It's just the items that continue to move across boundaries are going to be items that are highly enough valued by the people that the commerce still occurs. And so we can use taxation or tariffs to influence a system, but not totally control it. And if you issue the levies high enough, then yeah, you're going to control the system. Basically, you can shut it down and it'll fail. And there's a lot of other aspects in that. The tax code is a good example. A lot of people will avoid particular behaviors to avoid paying taxes on it, when if you look at the economics of that, it's more an emotional influence because they don't want to pay taxes rather than it being a financial influence. Things to review. Once we made a decision, we need to know if we control or just influence the system, because that in turn has an impact on the feedback component, which is fed back into the decision-making process. We have tools to support the decision-making. Those alternatives have to have some way to be valued, and we have to have some way to rank the value and a policy to guide how we select which alternative. The challenge of water resources management is fairness, defining alternatives. So we have to present a decision point. The resource we're making decisions on is scarce, so there's not enough for everyone that wants it, hence the need for this concept of fairness. And decision making itself is very emotional. So that concludes this component of the lesson. I hope you enjoyed it and have a good day.